We have two more speakers to finish out the day. Our next Gilbert lecturer is Dr. Brian Post. Brian is a senior research staff member and group leader at the Manufacturing Systems Design Group at Oak Ridge National Laboratory. He has been a technical leader on all of Oak Ridge large-scale additive manufacturing research. This includes the Big Area Additive Manufacturing System, BAM, I think, which was used to make the world's first 3D printed car, the Strati, and the Oak Ridge 3D printed Shelby Cobra. Oak Ridge also has also used the system to create submarines. This is 3D printing we're talking about now. Submarines, wind turbine blade molds, a mobile home, and the production tooling for precast concrete installations. Brian's team is now developing a rapidly deployable cable-driven 3D printer for printing concrete objects at construction scale. Brian will address current and future capabilities for large-scale 3D printing of industrial materials. Please help me welcome Brian Post to the podium.
Okay, well, I have a really hard act to follow, but I think that this is a really excellent opportunity. I'm super excited. It's not every day that you get to address some of the most respected engineers in the world and the next generation of young, talented engineers to come. I think I have one of the coolest jobs on the planet, that's a lot to say in a room full of National Academy members and also my colleagues. Maybe Bo doesn't count because his stuff is not on the planet, so that's a little different. But what I want to start, and I think what's really exciting about the work that I get to do is I get to work with some really talented interdisciplinary engineers on solving today's manufacturing challenges, right? And so manufacturing is a really interesting area, especially given our place in the world. So I want to start by asking you a question. All right, so maybe we'll start with the National Academy members. How many of you, when you were in primary school, had a class that looked like this, right? Where you had somebody that was instructing you on how to mold raw material feedstocks into end-use components, right? All right, almost all of wood shop was a favorite, right? Metal fabrication, those things were taught in school. And how many of the students have had classes like this or are going to have classes like this? Right, so as a proportion, and that's actually really inspiring because from my perspective and experience, because I was interested in going to college, that opportunity was not afforded to me. Right, I had to go to take a bus to another vocational school if I was on the technology path. And so if you look at the way that we've, as a society, thought about manufacturing, right, we've said, okay, it's a dirty, dangerous, and difficult profession. Making things isn't something that the U.S. is that interested in anymore, right? And we've started to see that show up in things like the trade deficit. Right, and I think we've all seen nowadays, right, in the last 3 years, how many of you have tried to buy something that you couldn't get or that it took a long time for you to get? That's almost everybody, right? Toilet paper, right? Everybody remembers toilet paper, but we've become really reliant on these long, fragile international supply chains, right? These opportunities for us to make things domestically have kind of disappeared. And you see that impact across all of the different sectors. If you look at like manufacturers and you say, how many of you experienced a delay that caused a significant impact in your business? Like this is just last year, it was like 70% for a given week. So it's becoming a bigger and bigger problem. And I think that's an opportunity, right? So what I want to challenge you guys today is that manufacturing is an opportunity for you. Right, it is where we need to go. So if you take some of the most critical things that we're working on and that we need for the success of our nation, right, we aren't able to source all of those pieces domestically. So take, for example, wind turbines. almost all of the wind turbines that we get, all of the pieces are manufactured internationally, and then we assemble them here, right? That's the blades, that's the nacelles, that's the generators and gearboxes, that's the tower structures, right? And so we have to ship those internationally. That's a huge carbon problem. So when you're taking these systems that are going to be renewable energy and cleaner energy, and then we have to ship them, these giant heavy castings from China, that takes some of the benefit away from them. And if you look at across our national security complex too, that becomes a problem. So these are huge challenges that we have. Now, why am I optimistic? Okay, so out of the students, how many of you have access to this, something like this? It's almost everybody, right? This has become the new entry point for students to learn about manufacturing technologies, right? So if you look at traditional castings and forgings and machining and those kind of operations, most of those opportunities in the United States to learn about those things and become introduced to them through your primary education have gotten diminished, but 3D printing has become a new technology and been democratized in such a way that most of you have access to it, right? And so this is really exciting, right? This is an opportunity space that we can get into. So my challenge to you is that, this is where the starting point, right? I want to show you that you can actually use this to make real stuff that has impact and that we can use. And I think it's another tool in the toolbox of manufacturing, but it is the gateway from which you guys can launch your careers in manufacturing. Okay? So I'm going to start talking about some different types of 3D printing technologies. And I want to start with some assumptions, right? And this is modern day manufacturing of 3D printing structures. We always say that 3D printing is exquisite. We can make really interesting things. Take, for example, this is a titanium robot hand that we built, right? And so it's got this lattice structure, and it's got an embedded hydraulic system. And so the pump goes in here, and you can actually flex these fingers by turning the hydraulic system on and off and using this pump, right? It's precise. You can make things that are very accurate. This is actually a bracket that is now in a nuclear reactor, right? So we're able to create materials and processes and qualify and certify them that can go inside of some of the most demanding applications on Earth, right? It's optimized. Right, so this is a good example. This is a carbon sequestration system for coal-fired power plants. So you have a fluid that's coming in and then dripping down, and this complex surface makes the path really tortuous. So you have lots of mixing opportunities for the gases that come in and mix with that fluid, and you're also simultaneously using it as a heat exchanger to extract heat from that gas so that those fluids can work more effectively. So really complicated structure, right? So you can optimize, and it's multifunctional, right? So we can actually do things like, this is a single block of metal, right? Which we've introduced the energy in such a way to change the grain structure and orientation of those structures within the block so that even though it's a monolithic material, if you look at the microstructural map of that, you get the Mona Lisa, right? So this is just changing the energy input and the materials throughout the structure. It's the same material, right? So we have the ability to really control material properties in a way that you couldn't before, right? But if we think about the way that industry treats 3D printing now, we would say that it's expensive and it's slow, right? And so those are the major drawbacks. And I say that if we accept those assumptions as they are today, we're missing out on the potential future of these kind of processes. So if you ask me what I want to be when I grow up, I actually want to be Elsa, okay? I think that what we want to achieve is the ability to really build with no size limits, right? She's fabricating this thing out of thin air, right? Achieve instantaneously high build rates with unbelievable material properties, unlimited geometric constraints. This is a really hard thing to build traditionally, right? And we want to do it for little to no cost. Right now, she's fabricating out of thin air, right? But I think we can use some materials that are more realistic. But this is really where we need to go. So how do we get closer to her vision and her dream, right? So we can look at existing processes, right, that we have that are these conventional manufacturing processes and see how they're applicable to 3D printing technologies. So, for example, This is a polymer extruder. You'd see one of these inside of an injection molding machine or in making tubing or things like that. These are the feedstocks for that process, right? They're polymer pellets. Most of the 3D printers you're probably familiar with use wires. Right, so imagine that wire chopped up into little pieces. That's what the feedstocks are for these polymer machines. These are inexpensive, $1 to $10 a pound pretty typically. Or we can use MIG welding processes or other types of welding processes and materials like wire, which are less expensive than the powder feedstocks that we use for 3D printing today in most of the cases. Or we can even use things like concrete. If you look at the materials we have available for 3D printing, right, most of them are in the $1 to $200 a pound range. Concrete's 3 cents a pound, right? So there's opportunities in going to lower and lower cost systems. And then we partner with industry to understand what the key needs are, what the key drivers are for the technology, and what the fundamental limits are. And then build systems that make sense for the different processes. So these are all systems that, I'll show you some of them, all systems that we've built in partnership with industry and then commercialized so that they can go out and make real-world impacts. So the first one I want to talk to you about is on the large-scale polymer side, right? So this is a process we call BAM, Big Area Additive Manufacturing. What we did is we took conventional extrusion technologies for polymers and a robotic CNC machine. This was actually a laser cutting system, and we put those two things together, wrote all the software we needed for it, figured out how to generate the tool path to execute this large object, and then we pushed ourselves for this moonshot to print a car. Right? And do I think everybody's going to be driving 3D printed cars? No, right? But it was an application that allowed us to push the boundaries of what was possible, right? And from that, we learned a lot of stuff, right? Let me give you an example. What we're printing is black, right? And the car is black. Why do you think the material is black? Anybody have an idea? Cheap? It's not because it's cheap. Anybody? Carbon. I heard carbon. All right, so we put carbon fiber in it, right? And why would we want to do that? It turns out that when you print something, or when materials are really hot and they get molten, they expand, right? And when they cool down, they want to contract, right? And they want to shrink. So if you have a cold layer that's already contracted, and you put a hot layer on top of it, and as it cools down, it wants to pull on the previous layer. So if you ever 3D printed something, you start to see like little pieces come up on the corners. That's what's happening. Carbon fiber has a very low coefficient of thermal expansion. So it doesn't expand very much when you heat it up and doesn't contract very much when you cool it down. So we take out a lot of that polymer, we replace it with carbon fiber, then it shrinks less and allows us to build larger objects without as much distortion, right? So a lot of the material you'll see we're printing is black. Right? We've actually been working with the University of Maine recently on biomaterial printing. So we're printing stuff with bamboo fibers and with wood flour and other things that go in there to perform the same function as the carbon, but are less expensive and give us and combined with a compostable neat resin, give us something that can be recycled or reused. Okay, and then this was the first car, and then a short 4 months later, we printed this car. Right, so the opportunity to improve and keep working on what you're doing is always there. Okay, another application space, and actually I was working with Karma on this back when she was at DOE. This is in precast tooling. So I said not everybody's going to drive 3D printed cars, but it can touch your lives in a different way, right? So this is the conventional process for making precast concrete. So you have a cabinetry shop that's employed to build these big molds, and then from that, you can get about 20 pours. So you can pour concrete into it about 20 times, and you can strip those molds, and then after that, the concrete forms start to fall apart, and you can no longer use them. So they were interested in, they had this specific application, I'll show you here in a second, whether or not we could 3D print some of these forms. Right? And so what we did is we actually used the large printer that we developed to print and then took it over and machined it to get a nice surface finish. And then these are the test formworks that we used, and Gate Precast did the actual pouring of the concrete, made a lot of these structures. And it turns out what it's for is actually this building in Brooklyn, right? And so this is on the old Domino's sugar factory location, and so this building is meant to look like a sugar cube. And so what that means is that they wanted to reflect light differently from each side of the building. And so the number of molds that they were going to need to accomplish this was measured in the hundreds, right? Because if they can only get 20 windows off of each mold, and they have, 1,000 windows, then they have to rebuild those molds a lot. So we were able to print about 40 of these molds, and they made all of the residential tower of this building using that. So if you're ever in New York City, look across the river into Brooklyn, and that's a building that was made through 3D printing, right? It's pretty cool. Okay, so that's polymers, right? We've done a ton of more things with polymer systems, but I want to move on to a different material system. This is metallic welding. So we're using conventional MIG welding technologies. They've been out there for a really long time, and a lot of interesting process control and toolpath generation. So we've got 3 serial robots, each with 6 degrees of freedom, and then a rotating table. So that's a total of, 19 degrees of freedom working together to try to solve an assembly problem, like Bo was mentioning, right? But each one of these is extruding material, welding directly on top of layer by layer, and they're collaborating. So we have a list of all the layers that need to be made, and all of the tool paths within a single layer that needs to be made, and they're being dynamically assigned to each of the robots, and they're taking a little sector of it and producing it individually. You'll notice as we get to the top, one of the robots will be removed. That's actually to balance the thermal history of the part to keep it from getting too hot so that it would collapse. And so we're able to start to build into these control systems the ability to modulate the process to achieve specific material property sets that we want. First demo we really did with this technology was building the arm of an excavator, right? So this gives you an idea of the scale in which we can build these things. This machine is capable of building stuff about 6 feet in diameter by about 6 feet tall, and there are now bigger versions of this kind of process that are being developed. We're currently working on one right now using electroslag strip cladding, which is a much higher throughput version. This will get us up to about 180 pounds of material an hour per head. So we'll be able to build large-scale casting replacements really fast. And the conditions of this bath, we think, give us the ability to do actually in situ reduction of iron ore. So we can create steel without a foundry process. So we can get near net shape, close to the final geometry of a low-cost casting for things like wind turbine applications. So if you need a hub or a bed plate casting. So there's a lot of opportunity in the large-scale metal space as well. Okay, so we've talked about polymers, we've talked about metals. I want to talk to you a little bit about concrete. Okay, so if you look at traditional construction technologies, this is from 1890. And this is my house when it was being built in 2016, right? It looks very similar, doesn't it? I think we, in the construction industry, we've kind of skipped a couple of the industrial revolutions. We should be able to bring some of that automation to bear. If you look at the cost of a car and the cost of a house, right? Houses are usually about 10 times more expensive than a car. And I'll argue that it's not because the house is more complex. Right? The car has, internal combustion engine that's converting, fuel energy into kinetic energy. You've got a climate control system. You've got multiple computers. It's a very complicated system, right? And your house is kind of sticks and rocks glued together and screwed together. But the reason why we can make cars more effective is the assembly line, right? And automation. And so we don't have that in construction. And so we started looking at opportunities to improve that. And there are people out there that are printing concrete and making housing structures with it. I don't know necessarily if that's the right application space, but it's an interesting technology that we need to start looking at. So we started from a little bit different perspective. We're robotics people, and we were interested in what is the appropriate robot system to do concrete deposition. And so what you really want is something that can adapt to the site, right? So construction happens on site. You want to have some system that can go out there and be useful in the specific terrain. And so we started looking at different kinds of robots, and we really came up upon the SkyCam. So how many of you have seen this before? I think everybody, this is like at a sporting event on a football field. It kind of flies over. Now, they don't have one of these per stadium, right? It's actually a company that goes around and does it at each of the stadiums, and they just pack it up and move it to the next one. So it's adaptable to the specific stadium. It's put up for a specific part of the game, part of the application, and they take it down and they move it to the next place. We really want to be able to do that with a concrete deposition system. And so we kind of said, okay, that's the SkyCam. Can we come up with SkyBAM, right? Something that allows us to do this large scale thing. And so we found this thing. It was a hang printer. It was a guy in Norway. And we said, okay, let's start there, right? And then we started looking at what the cable orientations might need to be, modeled the stiffness of the system and the configurations, figured out what the workspace might be, and then we figured out that if we change the cable orientations, we can actually get higher stiffness in plane, which is what we really care about. We want to be very accurate as we move and deposit the layer. And then we can also reduce the overhead to one single point. So you could have any kind of crane come out there and just hold it up in space. And then if we measure where everything is, we can compute the kinematics we need in order to drive this around very accurately. And that's what we ended up building, right? So we compute all of the cable lengths, what they need to be to reach any point in that space. But that gets us kind of close, right? So cables are long, they're stretchy, we don't necessarily know where they're going to be. So what we do is we actually use an auxiliary measurement system to shoot with a laser, reflector here, and then we use the time of flight of that to figure out exactly where that is in three-dimensional space. And then we tie that into the control system that's paying out the cables. So we can change it a little bit to make it more accurate. And when we do that, we go from errors that are over, about an inch down to errors that are in like the 30 thousandths of an inch. So very accurate over a really large workspace. And it's scalable. If I need to make a bigger one of these, I just add a little bit more cable, right? And if I need to make a smaller one, I just subtract a little bit more cable. And so this is a pretty exciting way to make these kind of big systems. I'll show you, so that you know it actually worked. I'll show you a version of our demo system. And so you'll see in the background some of these cable winding systems, and then this is the deposition head. We're feeding concrete down through this hose, and it comes out of this nozzle, and we orient the nozzle to shape the trajectory of the bead. Here we're doing a project we did with the Building Technology Office and FEMP, who's the main sponsor, Federal Energy Management Program, to look at smart wall structures. So imagine your wall was actually a thermal battery. So you have some thermal mass there. You can charge it at night by pumping cold water through it when energy costs are low and the building is unoccupied. And then as the day starts to heat up and you get people in your building and you start to turn on the HVAC system, what if we could shave the peaks on those demands by just releasing energy from this wall structure? And so we demonstrated this. It happened to be right at the beginning of COVID when we were doing this, so the people in the building were a problem because everybody was working from home. But we found one conference room that was being used a couple times a week, and so that's where we demoed this on. It actually worked pretty well. So we figured out how to do all of this, and now we're commercializing that system through a company called Orbital Composites. This is also something that there's interest in for using on non-terrestrial applications. So if you want to print something on the moon, right, rather than carrying this giant gantry robot up there, like the one we have at the University of Maine, we send something like this up there. It's a lot less mass to carry. They can be assembled and can do kind of the same job. Okay. Now, as we scale systems, right, we get larger and larger, right? In the natural world, we don't do that, right? So what we end up doing is dividing up the problem so that we can do it. If you look at a construction site, you don't just have one giant person that's doing everything, right? You have a bunch of people that are collectively doing things. If you do look at honeybees, right? You don't have one giant bee that's controlling where every little bit of material gets deposited. You break up the problem into smaller chunks, right? And so we're looking at these kind of class of systems that make things that are larger than themselves, right? So what we're looking at is, okay, we've been developing these big gantry systems. Can we actually make those individual agents? And so this is a robotic platform that can move in any direction at any time. So it can go left, it can go right, it can turn in space, and it can go diagonally, however you want it to. And then we've got a 6-degree freedom robot arm with a really heavy payload capacity, and then we've got one of those polymer extruders on it. And what we're doing is basically we can print, and then once the robot arm runs out of reach and it gets kind of bound, we can just like move the platform back, and then we can keep printing, right? And if we can keep doing that, then we can build things of basically unlimited size, as long as we know where we are in space, right? As long as I know where the robot is touching, then I can keep building stuff. And so we're using that same laser tracker that we figured out how to use in the previous project to do the recognition of where we are. And so that gives us an accuracy of about 0.003 of an inch over really unlimited workspace, as long as we keep registering the coordinate system. Okay, and then this is my last slide. So if we take that to its logical conclusion, we got really inspired by these drone lights displays. I don't know if you've seen those before, but imagine if instead of a point of light, each one of those is acting kind of like a mud wasp, right? It had a little bit of material, and it could bring it to the location, and it could deposit it, right? And it could form it. And so we started looking at actually flying drones and then depositing materials with drones. And so it's kind of taking that decomposition problem to the next stage. And I think this is eventually how we're going to start building these kind of large structures, by decentralizing the fabrication process. It's much more complicated, but it's much more inspired by nature, and I think that's how we'll get where we need to go. So with that, I am done with my presentation. Thank you so much for the opportunity to talk to you.
Hello? Okay. My name is Dan Dial from Cabrillo. And when you mentioned biological, when you 3D print with biological materials,
Yeah.
could you use, like, research that material and apply it to, like, realistic limbs, give it more like an elastic effect? Also with, like, organs, you know, how you could replace those organs with 3D printed, like, yeah, you know what I'm saying?
There's a lot of people that are really interested in that specific problem, right? How do we replace structures of the body, for example, or give new functionality to people who might be missing it, right? And so most of those have been in kind of like these lattice structures. So you create this kind of scaffold under which you can take cell growth and have it replicate over a structure. So you can create, done like ears and stuff and there are actually people looking at 3D printing meat, which is a whole thing. You know, that is an active area of research, especially in academia, right? We tend to live on the industrial side of that kind of equation, but it is a very interesting and open area of research that a lot of people are actually working on right now.
Okay, we have a question over here.
Hi, my name is Jade Pensado from Samueli Academy, and I'm a junior. I was just wondering, what type of motor does the Skybam or like the cable winding mechanism use? And is it reliable?
So they use electric motors, right? So they use what's called a servo motor. So it's a motor that can move, and then it has a little encoder on it. It's a little glass wheel that has some dashes on it. So every time it rotates past this little optical sensor, you can count one tick mark. And so you know exactly where that is in space. And then that cable winder is actually kind of cool. It slides back and forth so that the place in which the cable comes off the drum is always the same. And so we know by how many rotations we've done exactly how much cable we've let off of that drum. And so that's how we track that very accurately as we pay in and out the cable. It's close, but we have to use that external measurement system to get even closer.
Hi, my name is Michael Bradfield. I'm a junior and I attend Cabrillo High School. I was wondering, what are other products besides carbon that could prevent distortion in materials?
Okay, so you can add almost anything that'll take away some of the plastic, right? And carbon happens to do it really well because it's very stiff and has very low CTE, so a coefficient of thermal expansion. But you can use glass fiber. We're using cellulosic fibers. We're using bamboo, things like that. You can also use minerals. So there are lots of different options for things you can do. Putting different materials in the polymer is actually like just a wide open space that we're exploring. So one of the things that we were really interested in is like if you keep everything hot for a long period of time and it cools down uniformly, you get less of that distortion. So we like put a little bit of metallic particles in there, and then you can couple to it inductively and keep that whole thing hot. And as it gets higher and higher in temperature, the response goes down, and so you can actually set what that temperature is that it holds everything at. So there's lots of tricks you can play by adding these little things into it. And it's something that we kind of found through that moonshot. You go, I just need to get through this. I'm going to figure out what will work right now. Carbon is the most expensive thing, but it works. We're going to get to the end. And then you start to open up these areas of research, and those become really long-lasting and very impactful things that you can do that I don't know if we would have come across if we hadn't pushed really hard to try to get a car, right?
I'm Andrew Pervcacion, senior at Cabrillo High School. Could innovation in large-scale 3D printing improve speeds and pricing?
Of what we manufacture?
Uh-huh.
Absolutely. So, right now the material costs are probably a little bit more expensive, right? But if you start counting into things like transportation, right? If we're sourcing things internationally and we can source them domestically, and then there's real costs associated with like lead times, right? So if it takes me 6 months to get something and I'm bottlenecking the rest of my process, but I could make it today, but it costs 10 times more, there are times when those kind of trade-offs really matter, right? And so I think there are lots of opportunities. We've seen lots of places where that kind of impact is real. Often that's in like tooling, for example. So if you need stamping die to make car components, right? I can either send out for it and have it made internationally and it'll come in 9 months later, or I can make it right here. It might be more expensive, but I can make it quickly. I can add some additional functionality that I might not have had before, like conformal cooling right next to the surface of the tool. So there are different ways in which you can measure the impact or value of that kind of manufacturing.
Hi, my name is Santos Merito. I go to Cabrillo High School. I'm a junior, and I was wondering if you could like eventually 3D print like rocket ships or robotic arms, so that Mr. Bo could send them into space.
Absolutely. There's a company called Relativity Space right now that is taking that wire welding, MIG welding process and turning that into rockets. Right. We've done some. We've sent about 4 things into space in the last year, at really high speeds into really high altitudes that have been printed. Right. So it is not only a possibility as an actuality.
Hi, Carl Benjamin Vergado, a senior from Cabrillo High School, and regarding the never-ending possibilities of large-scale 3D printing, I was just wondering if it has the potential to truly replace traditional and current industrial and manufacturing processes currently.
So replacement of existing technologies, I don't think that's the right way to think of it, right? It's another tool in the toolbox, right? And it can be an expanding tool in the tool set, right? There's always going to be things that are better done through another process, right? But there might be specific applications where this is the right way to do it. And as engineers, it's kind of our job to evaluate the solution space, figure out what the right manufacturing technology is and employ it. It might be that additive is a way in which we can produce the tooling for that other application space. It might be another way that we can support it through packaging or other things. But it might be a piece of that puzzle that we need in order to solve the challenges that we have. For example, if there's a way to take really large casting and make it smaller castings, right, that we could do in an additive form or through support of casting processes that you can then assemble through an additive process. And there's lots of different ways to think about it, but I don't think it'll ever be a true drop-in replacement for every manufacturing process that we have. I think it'll keep expanding and expanding and being more useful and more useful.
Jacob Cervantes, senior at Assembly Academy. Would 3D printing houses help lead to more accessible and affordable housing options?
I think there are opportunities for housing in 3D printing. Right, everybody right now is kind of 3D printing wall structures. And wall structures are kind of like the fastest and cheapest things that we make about a house. Right, so I don't know if that's the right application space for it, or if we have the right material set that we need yet. But I think there are opportunities for, once you've figured out the automation piece, bringing in new materials and new processes to make real impacts there. There are some circumstances like disaster relief, right, when there's not a lot of capability for highly skilled workers to come back to an area to build housing. In that case, bringing in some more automation like 3D printing might make a lot of sense, right? But it's about balancing those different competing objectives to figure out where it really can be applied.
Well, last question.
Hello, my name is Joseph Bartash. I'm a sophomore from Samueli, and I was wondering, what do you think the future of 3D printing looks like?
Oh, that's a hard question. That's a really hard question. I don't think anybody really knows, right? There's places, and it really depends on the application sector, right? Castings and forgings, I think we got an idea of where that's going, right? We're going to do kind of large-scale metal processes. The polymer systems, we got kind of an idea. When we start to get to like space systems, I don't know, right? There's lots of things that work on Earth that might not work in space, and there's lots of, and so it really depends on what type of application you're trying to target, right? For me, I'm really interested in things like scaling laws, right? How big could we go, right? I don't think we've answered that. We keep coming up with new ways to like, oh, if I just use this process rather than this one that's existing, I can go a little bit bigger, right? But I don't think we really know where those things end yet. And so I think we're going to have to figure out what the boundary conditions are on that specific question, right? And then that's the job of us as engineers, is to figure out how to make the most impact that we can, right? So take a couple of those targeted applications and really work towards them, try to find out what all the problems are, and then address them one by one. So I don't have an answer, but I hope that helps.
Thank you, Brian. Thank you, Brian. You really do have an interesting job on Earth. And I have two questions for you, though. How much does that Cobra car cost, and what kind of deal can the president of the National Academy of Engineering get?
It lives up at the DOE headquarters now, so you'll have to take it up to the Secretary of Energy.
Okay, we can talk offline then. Okay, good. All right.